So we now start again a new lecture. So let me just, so we are at the end of rotational symmetry. So we looked at translational symmetry, which is from going from one, translating from one lattice bound to another, which is present in crystals. Second was mirror symmetry. The example of mirror symmetry can also be present in 3D or 2D. So here again you can see that you can have a mirror plane. For example, you can see in this case you can have a mirror like this, you can have a mirror like this, you can have a mirror like that, you can have a mirror like this. So there are, so in fact let me just basically you can have a mirror like this, horizontal mirror, vertical mirror, diagonal mirrors, okay. But in this case you can see on the right you do not have a mirror plane there, right. So you can have you have a mirror plane like this. If you draw a mirror plane, you have a mirror plane, but you can see the number of options of mirror plane have reduced. You have a mirror plane, but you do not have all the mirror planes as you see on the left. Similarly, rotational symmetry options have reduced because of motif. So what I wanted to emphasize at that point was, it is not merely the apparent shape that looks to you is important, it is the consideration of these criteria, whether it has rotational symmetry, whether it has mirror symmetry. These are important in defining a particular type of lattice or a shape. Now get back to third class. So this was again an example of reflection symmetry. So you can see that Taj Mahal is built in such a manner so that you have a mirror plane across Taj Mahal. So, but there are a lot of other objects which do not show this kind of symmetry, or our own human body, for example, has this symmetry. In case of human body, you can see that nature has made us fairly symmetric, so that you can draw a vertical mirror plane across us, and the left and right side, unless we have any physical deformity, we are fairly symmetric in nature. So now let us begin with lecture 8. So we have seen translational symmetry, we have seen reflection, we have seen rotation symmetry, and the fourth one is inversion. And inversion is an operation which is basically, let me now go to, so inversion is an operation. For example, I draw a cube here, so in the simplest of the in the simplest of the term, so this is a cube diagonal, all right. This is a cube diagonal. Let us say this is A, B, okay. So the center of the cube is the center of inversion, and you are basically bringing this point across in such a fashion so that you bring it to B. So basically your point x, y, z becomes minus x, minus y, minus z. So this operation is called as inversion, and this is an aspect which is found in 3D crystals, okay. So if I now come back to, so this is called as, inversion. So if I now come back to symmetry, 1D crystals show translation, reflection at best, okay. So they may only show translation, they may not show reflection, depends upon the motif. 2D has translation, reflection and rotation. 3D crystals have translation, reflection, rotation and inversion. So, T, R, this is rotation, T, R, let us say rotation and inversion. Okay. So, now let us get back to the crystals. So, in some sense let me draw a lattice now here. So, just to summarize now that particular point which I was trying to make. Okay. So, if I put a motif like this in this case, okay. So, it has a translational symmetry, you can see it has a translational symmetry, it has a 4-fold, it has a 2-fold, it has mirror plane like this. Let me just use a different color perhaps. So, it has a mirror plane like this. Similarly, it has a mirror plane in the other fashion. Well, okay. It has a mirror plane here and it has a mirror plane. Okay. So, these are the 3 symmetries you can see which are present. So, this is obviously case of 2D, and if you draw in 3D you will have inversion as well present. So, now what you can do at home is find symmetry in alphabets. What are the simplest thing you can do? So, you can try both Hindi and English alphabets. You will find that English alpha or Roman alphabets are let us say Roman. Okay. You will find that Roman alphabets are a little bit more symmetric as compared to Hindi alphabets. You can use common car symbols around you. So, you can see Honda. So, you will have Honda H, Volkswagen W and so on and so forth. So, you can try doing that and then anything around you. So, when you walk, just try to notice the symmetry. What are the symmetry elements that are present around you? So, now we come back to crystal systems. So, now we come back to basis of classification of lattices into crystal systems and 14 Bravais lattices. So, we saw that we have 7 crystal systems. And we have 14 Bravais lattices. Okay. We do not have of course 20. So, if I now say, so let us say I make 3 columns crystal systems, I make so of course you know the lattice parameter relation, I will not write that now, and then I write what is the defining symmetry. So, of course, it can be in a little bit more detail, but for the sake of this course which is very, so crystal systems are cubic, tetragonal, orthorhombic, hexagonal, rhombohedral, monoclinic and triclinic. Now, if I write the symmetry on the left, cubic has 4 of threefold, basically 4 threefold axis. I will come back to what we mean by this. Tetragonal must have 1 fourfold at least. So, 1 fourfold, if tetragonal does not have 1 fourfold, which could be there because of motif, then it is not called as a tetragonal crystal. Okay. So, for example, a cube, if it does not have 4 threefolds, even though it may look like a cube, it is not a cube. Okay. Similarly, let us go to orthorhombic. Orthorhombic must have 3 two-fold rotations. If it does not have threefold rotations, orthorhombic crystal, it is not an orthorhombic crystal. In case of hexagonal, you have 1 sixfold mandatory, and in case of rhombohedral, you have 1 threefold, and in case of monoclinic, you have 1, let us write 1 here, 1 twofold, and in case of triclinic, you have none. So, these are the defining symmetries of cubic. There is a lot more to symmetry. We write things like space groups, and because it is not only rotational symmetry which is taken into account for crystals, it is also rotational symmetry, mirror planes, something called as glide and screw, which are defined by basically atomic arrangement in the crystals. So, you write things like point groups and space groups for materials, but we do not have time for all that. So, what I just want to tell you that the basic criteria to define into 7 crystal systems is this: cubic must have 4 threefold. Anything else is possible only beyond that, only when it has 4 threefold. Okay. So, you can have further finer classifications into cubic system, but it must have 4 threefold axis. Tetragonal must have 1 fourfold, orthorhombic must have 3 twofold, and so on and so forth. So, these are the defining symmetry element for each of these. Now, let us begin with cubic. Okay. So, let us begin with cubic first. So, cubic, we know it is like this. Okay. And we can put the motif like this. This is the simplest and clearest motif. So, of course, we have here options of P, I and F. I discussed that in the last class. P is primitive, I is BCC, and F is FCC, face centered cubic. So, we can see that there is no end centered cubic, we will discuss that later. So, cube typically has 3 of fourfold. Let us write this 3 as 3. So, here, here and here, right, are the 3 faces are equivalent. So, it has 3 fourfolds. It has 4 threefold along the body diagonal. This is 1, this is another, right. Because it has 8 corners, right, 8 corners, so 2 of them can be connected with one diagonal. So, all these will have threefold rotation. okay, around that axis, 4 3-fold. And how many, it also has, by the virtue of it having 3 folds and 4 folds, it also has 2 folds. So, it has 6 2-fold, and those are nothing but, I will not draw it there, I will draw it separately. All right. So, if I connect this point to that point, yeah. So, if I connect this point to that point, and if I provide a rotation around that, it will be 2-fold. So, I have 6 of these phase, so this is nothing but a phase diagonal, right. So, equivalent to phase diagonal. So, 6 of these will provide you 6 2-fold rotations. So, these are written as here like this. Ovals, okay. So, 12 of these divided by 2 will be 6 2-fold, but the defining symmetry is this, okay. Now, so this is how cubic symmetry will be. In case of tetragonal, so I will give you just few examples, I will not get into all the details. So, tetragonal, so tetragonal, of course, we know that there is a primitive tetragonal and body center tetragonal. So, tetragonal will have one of 4-fold, and if you have 1 of 4-fold, it will also have 2 of 2-fold. So, that also you can see that if you, when you draw a tetragonal crystal. So, this is your tetragonal crystal. So, if you draw a line like that, so this is A, and C. So, this will give you a 4-fold rotation, all right. You will get a 2-fold rotation from here, 2-fold, and from another, which is this axis, 2-fold. So, this is 2-fold, 2-fold, and this is, and defining one is 1 of 4-fold. And similarly, you can see in case of orthorhombic and hexagonal. So, in case of orthorhombic, we have seen. So, I will not get into details of this. Now, I will come to the next point that we missed early, that we talked about earlier, is why do we not have 28 Bravais lattices.
So, what is the basis of these defining criteria for each crystal system?
What is the so?
Like we have all symmetrical cubic.
So this is the you can say minimum symmetry that is required. So you may have a 4-fold, you may have a 2-fold, but if you lose a 3-fold, it does not see, that is defined by motif. Okay. If you lose a 3-fold, it does not remain a cube. So, crystallographically speaking, a cube is a cube only when it has 4 3-fold rotations possible. Otherwise, it is not, it looks like a cube, but it does not give you the repetition of a cube, because remember, a cube must be brought into the position of self coincidence by performing the minimum symmetry operation. So, although 4-fold and 2-fold can bring it into a cube shape back into it, but 3-fold will not be able to. So, which means it has lost one symmetry element. So, that is the minimum defining. So, if you are able to perform a 4 3-fold operations on a cube, then 4-fold and 2-folds are automatic. But having 4 folds and 2 folds do not necessarily mean a 3-fold is automatic. So, that is why we choose the minimum defining symmetry. Okay. So, why do we not have 28 Bravais lattices? and we have only half of this. We can see we have only 14. So, what are the reasons? The reasons are, first reason is that is based on symmetry. Second reason is based on size. That is, the other possibilities convert into something else because of symmetry, because they fulfill the symmetry criteria of other lattice. Similarly, as far as possible, we must be choosing a smallest size with best possible symmetry. So, smallest size and best possible symmetry leads to other combinations, so that the possibilities convert into something else. So, let us see some cases for that. So, we have a crystal system table, and we have Bravais lattices, So, we can see that we have here cubic, again tetragonal, orthorhombic, rhombohedral, hexagonal, monoclinic and triclinic. Okay. So, we define these into the classes. So, let me write here P, I, F and C. In case of cubic, I have these two, tetragonal I have only these, orthorhombic I have all of them, rhombohedral only P, hexagonal only P, monoclinic has P and C, and triclinic does not have any of them, it has only P, nothing else. So, now first let us take the example, one example. Why is C-centered cubic missing? So, C-centered cubic lattice. Okay. So, let us draw the C-centered cubic lattice. This is the cube I am going to draw. All right. So, this is a cube which I have drawn. C-centered will be one atom here, another atom there. Okay. All right. Now, the question arises is, does it have, what is the defining symmetry? 4 3-folds. So, the question is, if I now draw a 3-fold from here to here or a 3-fold from here to here, does it have a 3-fold? Will I be able to bring it into self coincidence by performing a 3-fold rotation here? We will not be. So, what have we done here? We have lost the 3-fold symmetry criteria, 4 3-fold symmetry criteria. As a result, although it looks like a cube, it is not a cubic system. But then what it is? Is it a lattice to begin with? See, what was the definition of a lattice? This is point A and this is point B, both must have same identical neighborhood. So, we can see that B has 4 neighbors here, A also has 4 neighbors because one will be here, another will be here, another will be here. Okay. So, it is a lattice. So, what is it then? What can we reconstruct out of it? So, it must be something. So, what is it? So, what is it that we can now So, what we do is that we draw 2 unit cells. Okay. Okay. Now, let us put these atoms one atom here, one atom here, another here, and another here. If I construct, let us say, a unit cell like this, which is this yellow or sorry orange colored unit cell, what do you get here? It's a tetragonal. So, you can form a simple tetragonal cell which has a smaller size, So, end centered cubic is basically end centered or C centered cubic basically is nothing but a simple tetragonal cell. Okay. Similarly, so we can see that if I go back to previous slide, I can see that this is, so that is why it is not there, because it is this. So, we will see the other opportunity, other possibilities in the next class. So, basically just to summarize this class, we have seen that there are few defining symmetries in crystals: translation symmetry, reflection symmetry, rotation symmetry and inversion symmetry. These are followed in 3D cases, and as we have seen that Bravais lattices, crystal systems have certain defining symmetries, and then Bravais lattices are chosen out of those crystal systems based on their size and symmetry. We have seen one example, we will see more in the next class. Okay. Thank you.